In hover, Midnight uses around 1,000 horsepower in order to stay airborne, while horizontal flight needs only about 1/4 to 1/5 of that energy. Let's see how that works. When the aircraft is hovering, the full weight is solely carried by the propulsion system of the aircraft. This formula can be used to calculate the power required for the aircraft to stay at a certain altitude, where ρ represents air density and A, the rotor disk area. In a stable hover, thrust is equal to the aircraft's weight. Let's say that the cruising altitude will be 2,000 feet. In reality, Midnight will probably be climbing in horizontal flight, but for simplicity, we'll take a flight profile like shown here. Then we can calculate the density of air at 2,000 feet using the standard air density formula and filling in the numbers. The only thing missing is the rotor disk area. We can get that from the front of the Q3 shareholder letter. We know that the wingspan is 14.6 meters, then half of that is 7.3 meters. Using that scale, we can determine the diameter of the front and the aft propellers. Using some easy high school maths, we can then determine the rotor disk area. Now we have all the variables for the power equation. Plugging them all in gives us a total power of 472 kilowatts, or 634 horsepower. For horizontal flight, we begin by determining the thrust required to calculate the necessary power. Now, instead of the thrust, the lift is equal to the aircraft's weight, and the thrust is equal to the drag force. Given that the aircraft's lift-to-drag ratio is approximately 11.3, we can calculate the needed thrust. Using this formula, we can then determine that the total power required for cruise is 171 kilowatts or 229 horsepower, which is indeed around 3 times smaller than the power required for vertical flight. Although the computed value differs from the 1,000 horsepower cited by Archer, the difference can be attributed to factors such as parasitic drag, as the propeller arms block part of the disk area. Motor efficiency, as not all electric energy can be perfectly converted into rotational energy, and the aerodynamic profile of the propellers, as they also have a drag component working against the motor. So 1,000 horsepower is definitely possible for stable hover, and this isn't even when accelerating upwards.